Assuming this big boulder behind me doesn't decide to tip over and crush me, I think I'm ready to start this episode. And this will be episode 9. And this episode is on electromagnetism. It's the second of 3 that I'm doing in this series. And there's 3 of them because electromagnetism, this particular force, has a lot of variety to it. And I thought I'd spend some time getting into that variety. To start off with, because electromagnetism, the name itself is really long and has lots of syllables, I decided that instead of talking about that force and mentioning its name all the time, I'm going to use just the 2 letters EM instead, if that works for you. And if you don't like that, you can call my 800 number, customer service, which I don't have an 800 number or customer service, and you can complain to them if you like. But why don't we just get in here and then see what this whole thing EM is about in more detail. You may remember in episode 8 that I talked about the EM relative to electric fields and magnetic fields and magnetic induction. And if you don't remember me talking about that, no problem, because I can't remember my name half the time. But I did talk about it. But there's one particular area that I did not mention in that episode, and I did that intentionally because I wanted to talk about it in this episode. And that would be the EM's ability to manage and mediate electrons within an atom. Pretty powerful stuff, if you think about it. And if that sounds familiar to you, it's due to the fact that the strong nuclear force, it does something similar, but in a totally different way with protons and neutrons in the nucleus. And that was talked about in episode 6. So in this episode, what I'm going to talk about is I'm going to give you a little refresher on the strong nuclear force and how it deals with protons and neutrons. And then I'll get into the EM force in terms of electrons in this episode. And how I'll describe those, the EM, and how it does that, is in 2 scenarios. One being with an atom that's stable, and another example being an atom is unstable. And the analogy being with a stable atom, you can think of it like going on vacation, your flight's on time, weather's good when you get to your destination, room's great, food's great, weather's great, the whole 9 yards, it's great. So that's stable. An unstable vacation is whether your flight's delayed, the weather down at your destination is lousy, food's not great, kids are acting up, whatever it may be. You have, people next to you in the next room just making a lot of noise. Unstable type of environment. So you get the picture. Now, the one thing that you need to know is the strong nuclear force and EM, they're both operating within this tiny little area within the atom. And it's not unique. Fundamental forces can coexist together, and it's not a problem at all, and it happens all the time. The other thing is you have to realize, in context of the strong nuclear force and the EM and these particles, you have to realize that these particles are like incorrigible children. They're always getting into things, and they need some boundaries. And these forces really provide that boundary for them, as you're going to come to find out here. Let's get into it. Strong nuclear force. Here's a summary of the strong nuclear force. It is the strongest force in the universe, or one of the strongest forces in the universe. And it's primarily focused only in the nucleus. It's extremely powerful, but it's only within a really small area. Outside of the nucleus, it's basically, it doesn't have much power at all. So you think about how powerful it is in such a small force. That's pretty intense considering how much stronger it is than any other force. Anyhow, what it does, there's a variety of things that it does, but 2 things that it does is it basically is involved with the creation of protons and neutrons, and it also manages those protons and neutrons in terms of their interaction, sort of that interparticle relationship. In terms of the creation of protons and neutrons, each proton and neutron is made up of 3 quarks. Now, the quarks are different between protons and neutrons, that the variety of quarks, or they call them flavors of quarks, but each of them have 3 quarks. And these quarks are held together by something called a gluon, surprisingly gluon. So you have that dynamic of gluons holding quarks together. Quarks are comprising of protons and neutrons. So you see how the strong nuclear force is using those particles, quarks, and also gluons to build those protons and neutrons. So you get that tie. On top of that, you have the dynamic relationship between protons and neutrons and keeping them together within the nucleus. And you can think of this like to do this, there's a particle called a meson. And you can think of a meson like if you're familiar with a branch stem, and you grab some grapes and they're on these stems and they hold the grapes in place and provide some stability to that little branch. Same thing with mesons. That's exactly what they're doing. So basically, the strong nuclear force uses particles within the atom to create and control protons and neutrons. Clear as mud, hopefully? Good. We move on to the EM in the stable environment now. So let me throw this out there. You may wonder, why is it that electrons are orbiting the nucleus? And the answer to that lies with there's two sources for that. One being the natural EM attraction between the protons and the electrons. And then secondly, something called the Heisenberg uncertainty principle, which is causing the movement of those electrons. There's also a word used, or a phrase used, for the Heisenberg, and that is quantum mechanical uncertainty. They're basically dealing with the same thing. They're different, but the same type of thing. And I'll get into those shortly here. Well, let's set this up. We have the electrons outside of a nucleus, and electrons and protons, they just love each other. Like they love each other for life. They're like high school sweethearts. They just want to be together. So these electrons are trying to get into the nucleus to be with their proton friends. They want to bind. You felt that force, that energy when you put magnets together, the positive and negative ends of the magnet. They're like, they just stick together. They love each other. So there's that part of it where electrons are trying to get into the nucleus, but you have this Heisenberg thing going on. And by the way, Heisenberg, if that name rings a bell and you have seen Breaking Bad, the series, that's where Bryan Cranston, his name comes from in that series. So it's a perfect name for him in that series, which is a great series, by the way. But anyway, you have this Heisenberg thing going on where basically there's two aspects of it that drive the electron, that makes the electron move. One is the fact that the principle states that if you know where a particle is located, and I'm talking about at the atomic level that this applies to, if you know a more exact location of a particle, you know where it is, the less chance you know how fast it's going. And conversely, if you have a good idea how fast the particle is going, you have basically zero chance of knowing its location. Same thing, it's definitely applying in this situation too with electrons. The other thing that the principle, old Heisenberg, is dealing with is the smaller the space that a particle is in particular an electron, the greater the speed that particle will move. So if you think about the inside of an atom, that's pretty small. And the electron is small too, but there's not a lot of room in there. As a result of that Heisenberg, that electron is just buzzing around that nucleus at a tremendous speed. And I've seen different numbers, not that I've measured it myself, but different speeds as to how fast an electron's going. And the number that I keep on seeing is about 5 million miles an hour. Now you think about 5 million miles an hour in a tiny little space. That can't happen, but it's happening. So here we go. So you have the attraction between the protons and the electrons. So the electron is basically trying to dive bomb into that nucleus to be with its proton. And it tries to, but old Heisenberg comes into play, and that electron is traveling at 5 million miles an hour. So it's essentially what ends up happening is they balance each other out. In other words, the attraction that the electron has for a proton is offset by the speed at which the electron's going. So essentially, The electron is in a constant state of falling into the nucleus, but it can never get there. Definitely a different concept. However, it's not that unique. If you think about a satellite, for example, a satellite is really an object that is it's constantly crashing to the Earth. But due to its speed, it doesn't, because it just constantly never is able to get there, because the trajectory, the angle in which it's traveling, it wants to go in a straight line, and it never enters the Earth. If you've heard of centripetal force, that's what this is referring to. And if you have bored one day and you want to look that up, you can certainly learn about that. Now you see how the EM plays a part in keeping the electrons in orbit, that they're part of this process where they're drawing the electrons, being drawn into the nucleus, but that's being offset by old Heisenberg. Got that balance going on. Now, what I will say is, if you lost the Heisenberg part of the equation here, that electron would go right into the nucleus. If you lost the attraction between the proton and the electron, that electron would be flying out of the atom, because it doesn't have an opposing force to keep it in that orbit. So there you go. Now we move to an unstable atom. Now, mind you, what I just described applies to an unstable atom too, but there's other aspects of this where it makes it unique for sure. So let me set the stage for this one. Every second of every day, atoms are being bombarded by energy. My body is being bombarded by it right now, so are you. And this energy is caused by basically three things. One is heat. Another one is an electric field, and the third one being light. And all of those are energy sources. When they hit the atom, it impacts the atom, in particular the electrons. It doesn't really impact the protons and neutrons, because they're stuck away in that nucleus, and the strong nuclear force is so strong, it's like nothing's really messing with them at all, because of the strength of that strong nuclear force. But the electrons, different story. When energy comes in, they absorb that energy, and that energy is like an electron drinking a high caffeine drink. They go sort of bonkers. They don't know what to do with this energy. So what they end up doing, now here's where it gets really interesting. They jump to a different orbit level. Now, you probably are saying, I didn't even know there were different orbit levels. And if that would be the case, I haven't told you, so that's fair enough. But in summary, there are 7 different orbit levels in an atom. And some people use orbits, other people use the word shells, other people use energy level. They're all the same type of thing. But essentially, when an electron gets to absorbs energy, it jumps up to an energy level that's commensurate with the energy level that it absorbed. So you have this situation where if a little bit of energy is absorbed by the electron, and it's the right amount of energy, it will go to the next energy level. And if it's a lot of energy it absorbs, it'll go to the outer one, which is the 7th energy level. So you sort of get that tie there. So let me back up again and talk about this. Now let's talk, I'll describe how the EM gets involved. Energy comes in, let's say some heat hits the atom, the electron goes a little bonkers, it absorbs that energy, and what it does, it on its way to traveling to the energy level that it's heading toward, it causes basically a disturbance in the EM field within the atom. And this notifies the EM going, uh-oh, there's something happening here, and this something is messing with the stability of the atom, and we can't let that happen. So here's what we're going to do, me and you, electron. So as it's traveling up, it causes that disturbance, and when the electron gets to the correct orbit, the correct orbit, what it does is takes an atomic dump at that time. And the atomic dump is basically all the energy that was absorbed initially that caused it to jump in the first place is dumped. And that dump creates a disturbance in the EM field, and as a result of that, a photon is created. Now, I've never mentioned photons before. If I have, I never explained them, and I'll get to those shortly. You have this situation where electron jumps, impacts the EM field, then energy is released when it does the dump electron, and then EM in conjunction with the electron, they emit a photon, that energy source, and then that electron goes back down to its original orbit level. So you can see the situation where these orbits, some of them hold electrons like it's their permanent home. Other times these orbits or energy levels or shells, they behave sort of like an Airbnb. They're there for temporary visitors for the time being, electron jumping, and then once it emits its energy, it drops back down again. So there's this crazy game going on there in terms of what they do. There you have it. That's how the EM gets involved with dealing with unstable environments too within the atom. You could see how it participates with the electron to deal with any of these instabilities. Now on to photons. Photons are fundamental particles, and fundamental, of course, means that it was created at the time of the Big Bang. And what the definition is, they represent a quantum of EM radiation. Now, when you hear the word radiation, most people want to run for the hills because you think of radiation associated with, let's say, a nuclear weapon, or radiation associated with energy generation at a nuclear power plant. But you have to realize not all radiation is bad. But the bottom line is photons make up all types of radiation. And there are 7 radiation types. Now, you might wonder, say, wait a minute, there's 7 radiation types, and there are also 7 orbits or shells within an atom. Is there any tie there? I don't think there is. I just think it ends up being 7, like a touchdown, an extra point. It's just sort of coincidental. But anyway, the 7 types of radiation are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Now, what's the difference between these 7? It deals with the frequency, the wavelength of that particular type. For example, I'm being hit by radio waves right now, and radio waves are these waves that are just, they're innocuous. They're long waves, they're slow waves. It's like do 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 do. And they're generated by, for example, when you listen to FM radio, there's radio waves with the FM station. On the other end of the spectrum, you have gamma rays, and these gamma rays are intense. And the reason why they're intense is due to the fact that they're like this. And they're high energy, and then if you encounter them, they can cause tissue damage, and I mean, they're nasty. They can cause death. So once again, it all depends upon where you are in the spectrum. Some are benign, others can be pretty nasty. And it all depends upon the situation in terms of how bad they can be. You might have you get your X-ray with your teeth. What do they put on you? They put on a lead vest to prevent that from happening. So it gives you a feel for, these things could be pretty dangerous if you don't watch them and the intensity of them. Now, in terms of how they relate to the example of an electron when it gets to the energy level and it does the dump and the photon is generated, the type of photon, that being one of these 7 types, depending upon how much energy it absorbed from the external source in the first place, will determine the type of photon that it emits. In other words, if a small amount of energy was absorbed by the electron, it would emit a radio wave type of photon. If it was tons of energy that it absorbed, then it may release a gamma type of photon. So it all depends. That's it, the end of the episode. So what you've learned is the fact that the EM in order to maintain the stability of an atom, manages electrons within that atom to make sure, along with the strong nuclear force with the protons and neutrons, that that atom stays intact. I'm done. Over with. Next episode is episode 10, and this one is the third episode on EM, and the focus is on the fact that EM generates all light in the universe. Until then, I'll talk to you.